Welcome to the discussion. Today, we're delving into the paper, The Ingredients for Robotic Diffusion Transformers, which tackles the challenges of combining transformer networks and generative diffusion models for robotic control. The authors present a novel architecture, the DiT Block policy, claiming significant improvements in solving long-horizon dexterous tasks. Let's start with the core problem. Why is combining transformers and diffusion models for robotics so difficult?
The difficulty stems from the inherent differences between these two approaches and the complexities of robotic control. Transformers excel at handling sequential data and long-range dependencies, but their training can be unstable, especially when combined with the generative nature of diffusion models. Diffusion models, while effective for multimodal action learning, often require careful hyperparameter tuning, which is particularly challenging in the high-dimensional space of robotic control. Simply combining them doesn't guarantee success.
The paper highlights three key architectural design decisions. Let's discuss the first, scalable attention blocks. What improvements did the authors make here?
The authors address the instability of transformer training by incorporating adaptive layer normalization, AdaLN blocks, inspired by Peebles et al.'s work on image generation. These AdaLN blocks inject conditioning vectors into the layer norm layers, effectively shifting and scaling the input vectors. Crucially, they initialize the output scaling projection layers to 0, AdaLN 0, which stabilizes training and improves performance.
This seems like a relatively simple modification, yet it yields a substantial performance boost. What's the intuition behind this improvement?
The AdaLN 0 initialization acts as a form of regularization, effectively initializing the noise network with identity skip connections. This helps the network learn more efficiently and prevents it from getting stuck in poor local minima during training. The adaptive nature of AdaLN allows the network to dynamically adjust its normalization based on the input context, further enhancing stability.
The second key decision involves efficient observation tokenization. How did the authors approach this problem, and what were the key findings?
The authors compared different methods for tokenizing multi-camera observations, including vision transformers and RESNet encoders. They found that a relatively simple approach using RESNet image tokenizers combined with a transformer policy provided a substantial performance improvement, 40%, over competing strategies. This highlights the importance of leveraging the spatial priors inherent in CNNs, especially in data-scarce robotics scenarios.
This is interesting, as vision transformers are often favored for their ability to handle high-dimensional data. Why did RESNet S perform better in this context?
While vision transformers are powerful, they often require significantly more data to train effectively. In the robotics domain, data sets are frequently limited. RESNet S, with their inherent spatial inductive biases learned from extensive image datasets, provide a strong starting point, allowing the transformer to focus on learning the temporal dependencies and control aspects.
The paper culminates in the DiT Block policy architecture. Can you summarize its key components and how they interact?
The DiT Block policy integrates the best performing components: separate RESNet 26 encoders for multi-camera observations, a pre-trained Distilbert model for text goal encoding, film layers to incorporate text goals into visual features, and the AdaLN 0 attention blocks within the encoder-decoder transformer architecture. This combination allows for scalable, goal-conditioned policy learning.
The authors introduced a new dataset, BiPlay, for evaluating their model. What makes BiPlay unique, and how did it impact the results?
BiPlay is a large-scale, language-annotated dataset of bimanual manipulation tasks with randomized objects and scenes. Its diversity in scale, 7C23 clips, 10 hours of data, allowed the authors to assess the scalability of their model and demonstrate its improved performance compared to baselines trained on smaller, less diverse datasets.
The results section shows significant performance improvements over state-of-the-art baselines. Can you highlight the key findings?
DiT Block policy outperformed existing methods by an average of 20% across 5 tasks and 2 different robot morphologies, Aloha and Franca. This improvement is attributed to the stable training enabled by the AdaLN zero blocks and the efficient observation tokenization using RES-NetS. The model also demonstrated better scalability with the larger, more diverse BiPlay dataset.
The ablation studies are crucial for understanding the contribution of each component. What were the most significant findings from these studies?
The ablation studies confirmed the importance of the AdaLN zero attention blocks and the RES-net-based image tokenization. Replacing the AdaLN zero blocks with standard cross-attention mechanisms resulted in significantly less stable training and reduced performance. Similarly, replacing RES-NetS with a transformer-based encoder led to a substantial drop in performance, even when increasing the model size to compensate.
The paper also demonstrates generalization to a different robot morphology, Franca. How significant is this finding?
Generalization to a new robot is a strong indicator of the model's robustness and adaptability. The fact that DiT Block policy achieved state-of-the-art performance on the Franca robot, despite differences in morphology, action space, and observation space, underscores its potential for broader applicability.
The authors also conducted a simulation evaluation. How did the results compare to real-world performance?
The simulation results showed that DiT Block policy performed comparably to the baseline Diffusion policy transformer on the RoboMimic benchmark. However, the significant real-world performance gains highlight the limitations of relying solely on simulation for evaluating robotic control policies. The sim-to-real gap remains a challenge.
What are the key takeaways from this research, and what are the potential future directions?
This research demonstrates that careful architectural design choices are crucial for effectively combining transformers and diffusion models for robotic control. The DiT Block policy provides a robust and scalable architecture that achieves state-of-the-art performance. Future work could focus on further improving scalability, exploring different diffusion model architectures, and extending the approach to more complex tasks and robot morphologies. The open sourcing of the BiPlay dataset is also a significant contribution, paving the way for future research in this area.
This has been a very insightful discussion. Thank you for sharing your expertise.